Hi everybody. This short lesson starts by introducing the concepts of covariance and correlation, which are measures of linear dependence between two random variables. We then discuss the Cholesky decompositions of a symmetric positive definite matrix, and these decompositions are useful for the generation of random vectors with a given covariance structure. After that, we will introduce the notion of moment generating function, and we will see how these can be used to compute the mean, variance, and higher moments of a random variable. We'll also discuss some properties relating to independence. So let's start by introducing the notion of covariance. The covariance measures the joint variability of two random variables. If x and y are two random variables with respective means μx and μy, then their covariance is defined as follows. It is the expectation of the product of x minus its mean times y minus its mean. A simple bit of manipulation using the properties below will show that this can also be written as the expectation of the product minus the product of the expectations. We will leave this as an exercise. By definition, the covariance between x and y is the expectation of the product of x minus its mean times y minus its mean. That means that if the covariance is greater than 0, or equivalently, if the correlation is greater than 0, then we expect the random variables x minus its mean and y minus its mean to have the same sign, i.e. either both positive or both negative. In particular, if x is greater than its mean, we also expect y to be greater than its mean. Similarly, if x is less than its mean, we also expect y to be less than its mean. The opposite is true if the covariance is negative. In that case, if x is greater than its mean, we expect y to be less than its mean. Notice that we also denote the covariance of x and y using this sigma over here. Now here are some basic properties. Firstly, notice that the covariance between x and itself is simply the variance of x. Moreover, it's obvious from the definition that covariance is symmetric. In other words, the covariance between x and y is the same as the covariance between y and x. It is also easy to show that the covariance between x and a sum y plus z is the sum of the covariances between x and y and between x and z. Next, the covariance between x and a constant times y is just that constant times the covariance between x and y. The same is true if we have the c multiplied by x instead of by y. These three properties here state that covariance is symmetric and bilinear. Finally, it is also straightforward to show that the covariance between a constant and a random variable is always 0. All these properties are straightforward consequences of the definition and are left as exercises. Note in particular that the variance of a sum x plus y can be decomposed as the sum of the variance of x twice the covariance of x with y and the variance of y. This is because the variance of x plus y is just the covariance of x plus y with itself. That follows from this property here. Applying the bilinearity of the covariance operator, that is the same as the covariance of x with x, the covariance of x with y, the covariance of y with x, and the covariance of y with y. And then using the symmetry, these two terms in the middle are the same, they're just both equal to the covariance of x with y. In particular, if x and y are independent, then their covariance is 0, because the covariance can be written as the expectation of the product minus the product of the expectations, and if x and y are independent, the expectation of the product is the same as the product of the expectations. It follows then that if x and y are independent, that this middle term here disappears, and thus that the variance of x plus y is just the variance of x plus the variance of y. Next, we introduce the notion of correlation. If x and y are two random variables with respective standard deviations sigma x and sigma y, then the correlation, rho xy, is a measure of linear dependence between x and y. It's defined as follows. The correlation rho xy is the covariance between x and y divided by the product of their standard deviations, and we can also write it as follows. If we reorganize this expression, we obtain that the covariance is equal to the correlation times the product of the standard deviations. Now, it is an important fact that correlation always lies between -1 and 1. Moreover, if the extremes are reached, i.e. if the correlation is either 1 or -1, then y will be a linear function of x. To see that correlation lies between -1 and 1, consider, for any lambda, the following. The variance of the random variable x minus lambda y is of course non-negative. It is also equal to the covariance of x minus lambda y with itself. By symmetry and by linearity, that can be expressed as the covariance of x with itself minus 2 lambda times the covariance of x with y plus lambda squared times the covariance of y with y. In other words, it's the variance of x minus 2 lambda times the covariance of x with y plus lambda squared times the variance of y. Now what we have here is a quadratic in lambda, something of the form c plus b lambda plus a lambda squared, where c is the variance of x, b is equal to minus 2 times the covariance, and a is equal to the variance of y. Moreover, this quadratic is non-negative. If you plot the graph of this expression in lambda, of this quadratic, you will get a parabola, and because it's non-negative, it doesn't cut the x-axis, and hence it does not have two distinct real roots. This means that the discriminant, in other words the expression b squared minus 4ac, must be less than or equal to 0. In this case, the discriminant breaks down as follows, as you can verify yourself. And when we take square roots, it follows that the absolute value of the covariance is less than or equal to the product of the standard deviations. Note that covariance can be negative, but standard deviations are always positive. When we then compare this expression with this expression here, we see that the absolute value of the correlation must be less than or equal to 1, which is precisely what this statement here says. Suppose now that the correlation between x and y is 1. We're going to show that in that case x is a linear function of y. Recall that the covariance is just the product of the correlation with the standard deviations. So if the correlation is equal to 1, then the covariance is just the product of the standard deviations. Define a real number lambda to be the covariance divided through by the variance of y, i.e. the standard deviation of x divided by the standard deviation of y. This will be a real number strictly greater than 0. In that case, the variance of the random variable x minus lambda y can be computed as follows. And if we substitute the value of lambda into this, it will amount to 0. In other words, x minus lambda y will then be a random variable with 0 variance. In other words, it will be a constant. Hence, there is some constant c such that x minus lambda y is equal to c, i.e. x is equal to c plus lambda y. And thus there's a linear relationship between x and y. Conversely, if x is equal to c plus lambda y for some constant c and some strictly positive lambda, then the variance of x will just be lambda squared times the variance of y. Moreover, the covariance of x with y will be the covariance of c plus lambda y with y, and that is easily seen to be just lambda times the variance of y. Hence, by definition, the correlation is the covariance divided by the product of the standard deviations. And if we substitute in the covariance, as well as the standard deviation of x and the standard deviation of y, it will amount to 1. And hence we see that the correlation between x and y is equal to 1 if and only if x is a constant plus a positive lambda times y. Similarly, if the correlation is equal to -1, then x will be a constant plus a negative lambda times y. Here is an easy exercise. Suppose that x0 and y0 are the standardized versions of the random variables x and y. In other words, x0 is x minus its mean divided by its standard deviation, and y0 is defined similarly. In that case, the correlation between x and y is the same as the correlation between x0 and y0, and moreover that is precisely the covariance between x0 and y0. In particular, correlation is just a special case of covariance. The correlation between two random variables is the covariance between their standardized versions. Let's build some intuition about correlation and covariance. Here we have a reasonably large sample of points drawn from the distributions of a random variable x and a random variable y. These are plotted as a scatter plot. As you can see, the random variable x is concentrated near 0, in other words its mean is 0, and the same is true for the random variable y. Now the data lies along this line here, and this means that if x is larger than its mean, then on average y is larger than its mean as well. The same is true if x is smaller than its mean. In that case, y is smaller than its mean as well, on average. And therefore, in this case, the covariance is positive. And since covariance and correlation have the same sign, we have a case of positive correlation. In the second graph here, x and y are uncorrelated. We have cases where both the value of x and y are larger than the mean, but we also have cases where x is larger than the mean, but y is smaller than the mean. Finally, here we have negative correlation. In other words, the data lies along a line with negative slope. I must stress again that correlation is a measure of linear dependence, as demonstrated by the previous slide, where when the data was correlated, it lay more or less along a straight line. It is not a good metric if there is nonlinear dependence. For example, if x is standard normal and y is defined to be x squared, then x and y are clearly highly dependent, because if we know x, then we know y. But it is easy to show that the correlation in that case between x and y is 0. I leave this as an exercise.